Okay, excellent. Can everybody hear me and see my moving mouse?
Yeah.
Yeah. Okay. Okay, good. Now, this is a new computer, and I hope it works better. So, good. Okay, let's get started. So, today we will continue to discuss the basic optics that will be very useful for our research. Okay, so in terms of logistics, all the others. Do you have questions? Do you have questions? Okay. If no question, let me continue. You hear me, right, guys?
Yeah.
Yeah. Okay, good. In terms of logistics, all the plan remains the same, and we will continue to have our lectures and have 2 more invited lectures. And we will not have class during the Thanksgiving time. And our final exam, final presentation will be December 4th and December 6th. Okay, so we are all on the schedule now. Now, in terms of the proposal for the midterm exam number 2, I have graded multiple groups already. There are only a few groups have not sent to me your proposal. So please send that to me, and then I can comment and send and let it, using my comment to help your projects. Okay. So make sure send that to me as quick as possible, because you will need to improve your project and then give the final presentation early December. So we have less than 1 month for the preparation, right? So earlier you get my comments better, you will prepare for the final presentation. And I hope the final presentation of all of you can show great improvement and greater science content in the project. Okay, so make sure do that quickly. And if you received my comments already, and if you still have questions, you can always ask me again, and then I can recommend to it for you. Okay, and I can repoint to you new reference or new suggestions for you. Okay, that's no problem. Yeah. Do you guys hear me?
Yep. Yes.
Yeah. Okay, good. Very good. So I think all of you are doing great job. So make sure that you learn well in the class and also have more discussions with me. Okay. Okay, good. So let's start, resume our discussion about basic optics. So in last lecture, we talked about the timeline and the discovery milestone list of the microscope, right? And then from now on, we can start to talk about the basics of the optics and how to construct those different microscopes. If we know the basics of the optics, then we can understand the underlying working mechanism of those different microscopes, and then we can also construct our own optical systems. So here, actually, in addition to the timeline, the milestone series I put in the previous slides, here are several books that are very useful for you to read independently. For the first book, I have the electronic version put on the canvas. You can use that. For the other two, I also have electronic version, but they are very large, so I don't want to overwhelm you. If you want, I can send to you. But for the first book, it's very easy to read, and you can read that first. Yeah. Now let's start to talk about the optics. Do you guys see my slides changing? You see the shared screen, the slides on the full screen, right?
Yeah.
I see it.
Okay, that's great. Yeah, good. Okay, so whenever we start to learn optics in the physics, we actually start from the most basic concept of optics. If you want to dissect, categorize the optics in the physics in different domains, you actually will find they have 4 domains, and they actually cover each other, overlapped to some extent. The first most fundamental category of optics is ray optics. This I believe all of you have learned in the high school and in the undergrad during the early years of undergraduate study, right? So you will learn the light is go like a beam, right? Like a ray. So that's called a ray optics. Using this optics, fundamental optics knowledge, we can understand how to form images, how to set up optical elements in a lab, like where should you put the lens, where should you put the mirror, and what's the distance between the lens and the mirror, and how to adjust the angle of the mirror so that you can change the direction of the light. All those fundamental experimental skills, actually rooted from ray optics. If you understand ray optics, then you can use that. Okay. And then, as people discovered, the light is not only the ray. The ray optics is actually coming from the knowledge, the theory that light is made of the particle. Okay. But then later on, people find light is not only particle, light is also a wave. So then people developed the wave optics. So you can see the green ring, green ring, actually it's green circle, okay, green circle that covers the ray optics. So wave optics, it covers more knowledge about the optics. That using the wave optics, you can put the light together and form the interference, okay, so that the sum of the light can be canceled out, some light can be strengthened. Okay, so that's because of the light is light propagate following the wave properties. Okay, and the wave property also contains the particle property of the light. Okay, so they are not conflicting to each other. Wave optics is even larger, even broader. Okay, so using the wave optics, we can build upon the basic microscope. We can design the microscope such as turf microscope. We can let the light reflect at the bottom of the petri dish, and then what total internal reflection, and then that reflection actually is also generate a transient wave. Okay, evanescence wave. It's called evanescence wave. That wave can penetrate through the glass bottom petri dish, go upwards, and then using that wave, we can measure the fluorescence at the interface of petri dish top surface and bottom surface of the culture media. Okay, so we can see very hundreds nanometer distance fluorescence. So that provides very good optical section and provide important information at the bottom of the cell, such as the integral, right? Such as integral and also the bottom membrane, right? So that actually is the utility of the wave optics. Even further, people find the light is electromagnetic wave. It's not just like a mechanical wave, electromagnetic wave. And then the light also contains the polarization, right? So light has polarization. Using this property, we even expand the knowledge of the optics, and then we can develop a polarization microscope. Those kind of microscope is very useful to look at the cells or the biological entities that have theoretical structures. So, for example, we talk about the collagen, right? Collagen, and we also talk about the cytoskeleton. Those are all polymers. Those polymer has a very unique feature. Their surface has theoretical structures, right? They have different monomer connected together. Those structure can be very easily distinguished by the polarization microscope. Okay, so that needs the electromagnetics understanding of the optics. Now, if we expand even further to the quantum level, then we will understand the quantum mechanics, quantum optics. Okay, so we will start to learn the photon in the optics, like a single photon. Then from there, people using that knowledge, people can develop a fluorescent microscope. Okay, so we have a one photon fluorescent microscope. That means only one photon is used to form a pixel in the imaging plane. Okay, there are also two photon microscope. That means there are two different photons. They collide with each other and then integrate into one photon. So then their intensity, their wavelengths changed. Their intensity also changed, but and that form one pixel on the microscope, detection chips. Okay? That is a two photon, the basics of a two photon microscope. There are also three photon, four photon as well. Okay, so all those different multi-photon microscope are very useful to look into deep tissue biology because they usually contain very long wavelengths. Usually it's red color or far red color. Okay, and then when the two photons collide together, they integrate together into a new photon. That red color, because red color usually is 800 nanometer, right? 600 to 800 nanometer. If two photons connect together, become one photon, their energy is added together, and the energy of the photon is linearly proportional to the frequency of the wave, frequency of wave. Then the energy increase, frequency increase, and then the wavelength decrease, right? Wavelength decrease because speed equals to wavelength times the frequency. Then the wavelength decrease. So then that two red color photon will become one blue color photon, right? So that can be easily detected by the microscope. And then the red color light can penetrate deeper into the tissue. So that help people to study the deep tissue physiology there. Okay, so based on this is the overarching picture, shows 4 different categories of optics, and then each category, the knowledge can be used to develop the corresponding microscope optical system. Okay, over the years, people actually developed many different types of microscope that can see different, depending on the need. They can see different. They are used to see different biology samples. Okay, and then they see, even for the same sample, they see different features, different parameters of the biological sample, such as the cells. Okay, do you guys see my screen and see my mouse?
Yep.
Yes. Yep.
Okay, very good. Now here is some example of different modality of the microscope. Okay, so the key of the microscope is to see the tiny things, to magnify the tiny things. And why it is magnify those tiny things, they also need to let us see that tiny things clearly, right? In order for us to see those tiny objects clearly, the tiny objects need to have some contrast compared to the surrounding. They need some contrast. Otherwise, if the tiny thing is the same as the external environment, then we cannot tell where is that tiny thing, right? Where is that cell? So usually those microscopes not only magnify things, but also use the light to provide some contrast of the cells. Okay, so here are several modalities. So I don't have time to talk about all of them, but I will give you some example for the initial several of them. So first one is called a bright field microscope. You see my mouse, the bright field microscope. This is the most fundamental microscope. It can magnify the cell and also use they actually direct all the light from the top to the bottom, go through the cells. Okay, so this microscope is not that efficient to tell the features of the cell without any additional support. Those additional support is coming from some dyes. Here you see the color here. This actually is a traditional staining. This dye means dye is used to do the staining of the cell. So here, this cell is a stand using the dyes. That's called HE dye. Okay, so H and E, they are two different chemical. HE, E is used. E is called ison, the dye that is used to stain the nuclear. Okay, so the nuclear will become purple. H is another chemical. Okay, that is used to stain the extracellular matrix or cytosol, non-nuclear region, and then it will give the pink color. Okay, so once those two dye combine together, put on the cell, then the cell will have color. They will have a pink color and purple color, and the combination of those colors. Okay, then we can use that to tell where is the cell located and where the cell is behave differently in terms of the morphology. Right? If there is a tumor, then it's very easy to see that in certain region you have a lot of purple color, many purple nucleus there. So it means the cell is over proliferating. That's always a hallmark of the tumors, right? So this HE staining is always used to look at the histology of the tissue. So using that, the bright field microscope can tell the cell structure there. Okay, so that's bright field microscope. But when you add the staining, when you add the dye, usually you will cause the cell death. You need to fix the cell. So bright field microscope is not that good to see the features in a living cell. For the dead cell, with the help of the staining, then you can see very good images. But then that's just one snapshot. Okay, we always want to see the dynamics, as I showed it previously in the last lecture. You want to see the structural dynamics and the functional dynamics of the cell, right? So then we need a microscope more than just the bright field microscope. So the phase contrast is another one. Also the DRC, phase contrast and DRC, they are two different microscope that can see the dynamics of the living system. DRC is called a differential interference contrast microscope, DRC. Okay. So firstly, phase contrast microscope actually use this microscope can be built upon on the bright field microscope. So on the microscope, if you add some condenser, some element condenser onto the top of the imaging objective, those condenser can do the computation of the light. They can convert the changes of the light phase into intensity information. So when the light here, what we see is top view. If the light goes through those cells, here is 5 cells. Okay, those are the very normal cells. When the light goes through the cell, because the nucleus of the cell is thicker and more condensed than the periphery, like than the cytoplasm. Okay, because nucleus has contains very condensed chromosome, right? So they have a higher reflective index, means they can stop, they can postpone the propagation of the light phase better than the pure cytoplasm. Okay, and then cytoplasm, because it contains the cytoskeleton and other things, they have a higher reflective index than the surrounding water, surrounding culture media, right? So they have different, overall they have different reflective index, and also they have different height, because the high thicker sample, they also are more effective. They also postpone the propagation of the light better, right? So combine those things together, the nuclear region let the phase of the light get postponed even further than that in the cytoplasm. And then in the cytoplasm, that postpone the phase even more than the culture media. And then the condenser I just mentioned, they can convert those phase delays into the color, into the intensity, darkness of the signal. Okay, so then the nuclear become darker, and then the cytoplasm become less darker, and then the surrounding media become even less darker, right? So you can see that. And even within the nucleus, we have multiple location that contains a lot of transcription elements, right? So you can see those dots here. So those are even more condensed region within the nucleus. That is even denser region, which contains even higher refractive index that also can be translated into intensity distribution. Okay, so that's why using the phase contrast microscope, you can see very detailed features in the cell. Whenever there's small mass added into the cell, they change the refractive index, change the light phase, then it can be converted into the intensity information. Then we can quickly tell it. And then when the cell move, we also can see those dynamic change very efficiently. Okay, that's the good thing about the phase contrast. But it also has limitation. It is most suitable for the sample that is very thin. Okay, because the light can efficiently transmit through the sample. Okay, if the sample is very thick, light is not very easy to transmit through, then the phase contrast cannot give us very sharp images. Okay, so that's the limitation. Also, compared to the fluorescent picture, you see here. Do you guys see my mouse? Do you see my mouse?
Yeah.
Very good. Compared to the fluorescent picture, this phase contrast image only tell us the information of the refractive index of the mass distribution in the cell. It cannot tell you this mass is coming from the motor protein or coming from the cytoskeleton or coming from other organelle. You cannot tell. It only tell you the mass. If the two different organelle, they have the same mass, then they will show the same in the phase contrast. Okay. In the fluorescent microscope, we can exactly tag the specific organelle with the exact color we want. So then we know exactly what we are looking for. Okay. However, in the fluorescent microscope, because we rely on the color of the cell, fluorescence there, and the visible light spectrum is limited only from about 200 nanometer, the purple, to the 800, about the far red, only about 600 range, very easy to recognize. Then and our eye cannot tell that the green light from 500 nanometer to the green light from 550 nanometer. We cannot tell that easily. We can only tell this green color 500 from the red color from 600. That we can tell. If it's 100 to 200 nanometer apart, then we can tell from the color. Otherwise, we can, if it's very small, we cannot tell. So that means for the cell, if you use the fluorescent protein to label specific organelle, you at the most can label 3 to 4. Let them be 200 nanometer apart. Okay, only 3 to 4. So then that's the low throughput, only low number of targets we can observe at the same time, right? But the phase contrast, you can see everything. You can see everything. Okay. So usually, but we just don't know what are those things. Okay. So usually people combine these two together, phase contrast and the fluorescence together. So then you can switch between different modalities. Okay. Now, in the middle one is the DRC microscope. So this microscope is different from the phase contrast. It contains different condenser, different computational elements. That condenser is used to see the gradient of the refractive index and the gradient of the thickness of the cell. Okay, so gradient of two things. What does that mean? That means DRC is measuring the gradient, is measuring the differentiation. So it does the one-time differentiation of the function here. Okay, the function of the refractive index and the function of the height. Okay, so then what do we see here? The color, the intensity, light intensity we see here actually is showing us the slope of the cell. So when you see this, you see it's like a contour, right? What we see actually is the slope of the cell. Okay, the morphology, top surface morphology of the cell. That's also very useful because that information cannot be obtained in here. All the phase contrast image telling us is internal mass distribution. But here, DRC, we can see the surface distribution, right? It's not a mass distribution, it's a surface topography, surface distribution, and also it's a differentiation. And then in the fluorescence, we are actually seeing the identified, specified organelle. What's their dynamics, right? So those are they have different use. So far there are no microscope, no one modality can capture everything. We have to, in one microscope, you can establish multiple modalities, but you need to switch between back and forth. Okay. Number three, last three is Hoffman modulation. I don't have time to talk about this. You can read it here in this article. And then this one is called a dark field microscope. This is in contrast with bright field microscope. In the bright field microscope, we actually have light everywhere in the cell and in the environment, so that we add the dye to stain the cell, and we can generate a contrast. Okay, but if you don't have a dye, and you still want to see some feature, some cells that has a very low contrast with the environment, then you can choose this one, dark field. What does this mean is this microscope, the light is not perpendicular, not directly projected to the sample. It actually go in an oblique angle. So in the right hand side and left hand side, they have an angle. The light go like an angle, so that the light will hit the sample, and then let the sample scatter the light. But the environment, all the environment will not receive the light, so the environment become darker. In this way, actually, you can see really tiny feature of the sample by letting the sample itself emit out the sunlight. It actually is not emit out the light. It's actually let the light be scattered going towards the sample and get scattered due to the internal heterogeneous structure of the sample. Okay, but it looks like sample is emitting out the light. So then when something is emitted out of the light, then become very easy to tell the internal structure, right? So this microscope is very useful for small sample that is in a 3D, and such as very small shrimp. In the nature, they are very small shrimp that be eaten by the small fish. Those shrimp, when they migrate in the water, if you use dark field microscope, you can see all the details in the shrimp very easily. Okay, but for the sample that is thicker, like a piece of tissue, this method is not that useful. Okay, and also the polarization microscope. This I mentioned earlier. It's very useful for looking at the sample, the polymers that has a periodic structure. Here you see this extracellular matrix. They have a periodic structure, and you can tell it very easily. Okay, yeah. Okay, here I just list a few of them. There are actually many more. This is very rich now. There are many more modality that I can see can have different purpose. Okay, I have a table actually of all the microscope. In the future, I can send it, share that with you once you do if you do the research on that. Okay. Now to understand how those microscope works, we need to understand the basics of optics, right? So here are some review of basic optics you may have learned, but I want to strengthen it to let the concept to be understood deeper. Do you guys see my screen? Do you guys?
Yep.
You can see it. Okay, good. So here is talk about the principles of pinhole camera. What this means is when you have an object here, this object itself may not emit our light. Here is a little bit different. This one is the lamps. Okay, this can emit the light, but even if it does not emit out the light, the sunlight from the generate the light, sunlight, and other light coming into the object can be deflected, can be reflected, okay, and then can go to different directions. Those light propagate around straight lines, okay. If we put a opaque board in one position and then penetrate a hole there, the light coming from this object will go through this pinhole only when the light coming from it has the correct angle that it can let it go through the pinhole. Okay, only those light, not the light you see here dashed line. This line is not going towards the pinhole, then it get reflected by the opaque board, and then they cannot penetrate through the board. Okay, so only the solid light goes through the pinhole, and then once it goes through the pinhole, they can form an image there. Okay, this is the most fundamental image from the object to the image. Okay, and then this image is inverted. Okay, now here two things need to be correct so that we can see this image. If you put a camera here, if you put a camera here, then the chip, the light sensitive chip inside the camera, every camera has a chip. Okay, that is the most expensive part in the chip in the camera. Okay, when you buy the camera, most money you invested is for the chip. That chip has a specific density of pixel that determines the resolution of the camera, and also has a specific sensitivity that determines the grayscale of the camera and the minimal exposure time you can use to capture any meaningful images. Okay, so if you use a camera, then that chip, you put a camera here, the chip has to be in this position. Yeah, so the position here, this talks about position. This is very important, and also it only captures the part of the light reflected from the object, only the one going through the pinhole. That means the angle is also very important. Angle. Okay, so this angle and position, these two terms, we will talk about them again and again, because when you construct a microscope, you actually direct, especially the fluorescent microscope, you direct the laser towards the imaging object, and then you need to consider what's the angle, what's the position, so that you can let the light go in the way you want to hit the cell on the sample plane. Okay, so these two terms are very important: angle and position. Now, this talks about the important behavior of the light reflection. When the any light, the ray, here we are talking about the most inside circle, right? We talk about four categories. The first category is ray optics. Here, this is the basis of ray optics. Now, in a ray optics, if there's a ray of light going towards hit a reflective surface, then the light will get reflected, right? When it's reflected, the angle alpha I is called an incident angle, right? Angle of incidence, incident angle. This angle will be equal to the reflective angle of reflection, right? Alpha R. Alpha I and alpha R will be equal, right? So this actually is the principle people always use to make that judge where you should put a mirror in a microscope. Mirror is the perfect spectral surface. So usually in a company, okay, they coat the silver at the inside of the glass, okay, so then they can have perfect spectral reflection. So all the light get reflected, no energy loss, okay, all reflected. But in reality, there are other types of reflection. For example, if you have a sample like this actually tissue, biological tissue is very like this, biological tissue, some kind of biological tissue, especially like the tissue contains very diverse cell types inside. Then those different cells, they have different gene expression. So then they have different protein inside. And then if there are many of those cells together, the cell-cell boundary, membrane boundary they also contain different refractive index. So if you have that case, very likely you will have a perfect dual surface. So when the light goes through, light bump encounter those surface, it will not have a perfect reflection like in this angle. Okay, it have a portion of that go towards that, follow that angle of reflection, but other part, of the rest of the light will be reflected into different directions. The reason is because in this region they have a very heterogeneous refractive index and interface there. So they all can play the role like a perfect surface, but in different angles. Okay, so then the light is actually get completely deflected. Okay, so this happens a lot, and there are strategies to overcome this right now. Okay, in between these two cases, actually there are called a shiny plastic effect. So when the light reflects, most of them go towards the angle of reflection, but some of them still go to different direction, but their distribution is different. Okay, this mostly happen in our uniform organs tissue in the tissue. Okay, so the cell type is very uniform, and they also have varied reflection index, but not as dramatic as this case. Okay, so this one is always encountered in the bioimaging case. And in terms of the real optics, if the key point is we want to know how the real physical object can be captured by the optical lens, and then form the image in the correct way, form the image as we want. Okay, the image we want, in terms of the image formed, that image will be on the microscope chip. Finally, it will be imaged on the microscope chip and then converted into the digital pictures displayed in the computer screens, right? So that image, the final image on the camera chip, have certain properties that we care about. Firstly, what's the size of the image? Usually the microscope, we want to magnify the sample, right? So we want to get an image that is larger than the cells, than the object that we perceive by our naked eye, right? So we want to know what is the magnification, and then also what's the orientation. Some images upward, some are inverted, right? And also the types, real image or virtual image, right? So real image means the light will converge to form the image there. The virtual image actually is the light is divergent, and then when we see it, it looks like an image from the big. When we back extrapolate the light ray, then they form an image there. But that image is not the convergence of the real rays of the light. Okay, do you guys follow me?
Yeah.
Yeah. Okay. Very good. Very good. Let me know if you want me to go quicker or go slower. Okay. Okay. So here is one example about the ray optics. This is very fundamental but super useful. If you know this, then you can build a very fundamental microscope. Okay, without a mistake. Okay. So in this case, we have one object which is here, which can be anything. Okay, can be anything, and then this object what we want is to capture the picture of this object, right? And then to do that, we need to put a lens there. The lens, what is lens? Lens means there's a piece of glass, but the surface of the glass is not flat. If the surface is not flat, means it has curvature, then it can bend the light. By designing correct or appropriate curvature of the glass piece, we can manipulate how the light get bended and where the bended light can converge. Okay, that is the purpose. That is the purpose of using those curved optical element. Usually we call it a lens. Okay, If the curvature is positive, like this, means convex, right? So that, yeah, convex. So that is called a positive lens. Okay. For the positive lens, you can see how the light coming from the object get converged. Now, if we consider the top point of the object, we can consider three rays of light coming out from this point. One is going parallel to the optical axis. Optical axis actually is the line, the dashed line. This line is penetrated through the center of the lens. And then in this case, we are simplify this case, let the lens and object to be parallel to each other, and both of them in a vertical direction. Okay. Now the first light go parallel with optical lens, with optical axis, and then it will get bended because this is a positive curvature. So then it get bended. Okay. When it's bended, it will go through one. It will the penetrated light will intersect with optical axis. This point is called the focal point of this lens. Focal point. Okay. And then it will continue pass through it. Another ray of light is going through the center of the lens. For this one, it will not change the direction. It will change the position. Here is an optimized view. Actually, once it goes through it, it will shift back downwards, But when after it penetrated out of the lens, it will follow the same direction. Orientation is the same. Okay, just shift a little bit, and then it will go through the air, and then it will encounter the previous this ray. They will intersect with each other. The third lens will go through the front focal point of this lens, and then pass through it without any change, and then penetrate through the positive lens. After this, it will go parallel. It will go parallel with the optical axis. Okay, and if this lens is ideal, means that this lens, the curvature on the 2D surface. Okay, it's not a 1D, 2D surface on the front surface of this lens, 2D surface. The curvature is homogeneous everywhere. Okay, on different isotropic on all directions is correct. Then this three ray will be convergent into one point here. Okay, into one point here. So this point corresponding to this point, and this point is the image of this point. Okay, the same principle, three rays can be applied to any point of this object, any point, and then all of them will converge here, converge at point. After the convergence, they will diverge. Okay, but after they all converge here, okay, means all the light will be concentrated here to form an image of this object. This is called a real image. This is real image because the light really concentrated here. Okay. Now here is the location we put the camera chip. So the camera chip put here, the sensitive pixels on the chip will sense those photons coming out from the object, and then convert those photons into the electron. And then electron will get magnified. It's called EM, right? Electron magnification, EM. Many microscope for the single molecule experiment need a high efficiency to magnify the light, magnify the photon. They use EM GAN, right? So those photon converted electron will get magnified and then form and then be constructed by the computer to form the image, form the real picture. Okay, so here is the basics of the image formation in the ray optics. If you look at this lens, you will see it's a little bit strange. The one surface is curved, another surface is not, right? Or another surface is flat, right? This actually is a real. In the real experiment in the lab, if you buy the lens from the company, each single lens looks like this. They don't make both surface curved because this is easier easier and more manipulatable. Okay, can give us better convergence of the light. And when you assemble microscope together, you use those lenses, many lenses you use together, you always let this curved surface facing the emission, the excitation light from here, the incoming light. The incoming light usually we call it a collimated beam. Okay, so and then this curved surface is called curved surface. So this is called the CC principle. So always have this surface facing the incoming light from the laser. Okay. The reason is if you do it reversely, then the convergence is not as good as this configuration. Okay. And then in the reality, if you combine multiple of those lenses together, you can form a compound lens. They will multiple lenses together will behave like one lens. People always do that, the multiple lenses together, so that you can eliminate any small divergence here or any light diffraction there, the color diffraction there. Okay, so usually people don't use one lens, multiple lens, and all of lens when you put it together follow this CC principle. Okay. Now, when people design those optics and then fabricate these optics, the relationship between the focal length and the position of this image with respect to the lens is not random. It's not random. They actually follow the equation. Lens make equation. Okay. If we have the object that have the distance of L1 from the lens, then and also this lens has the focal length f, then we can absolutely determine what is the position the real image will be formed. We can know that. Okay, so that is determined by the physical properties of the lens, and also by changing the position of the object, we can change this position of the image. When we change that, because this is the geometry proportional, right? Geometrically proportional. When we change the distance here, we also change the size of the image, right? So then we can get a different magnification, because magnification is defined by the size of the image with respect to the size of the real object, right? So then these are connected together. Yeah, and then here, if you understand this, here I have some question to ask you. Do you guys hear me?
Yeah.
Yeah. Let me ask you some questions. So to test whether you understand it or not. First question is, what happens to the light from an object that is moving closer to the focal length? So if we have an object here, if it moves closer and closer to this lens, what will happen to the image? Can anybody tell me?
Will it get blurrier?
To the focal point.
Oh.
To the focal point.
The image will get sharper.
Sharper means what? Means the resolution.
The resolution will be better.
Resolution, we have not talked about it here. It has nothing to do with resolution. I'm only talking about the size, right? So tell me the size. If this guy go closer and closer to the focal point, how this image size become larger or become smaller? I think it would be better. Maybe I leave this question for you. So here are 3 questions. They are also in the PowerPoint slides in the canvas. You can firstly understand what I talked about today, and then see whether you can answer those 3 questions. Second question is, if the object is closer, if it pass the focal point and then go closer and closer to the object, to the lens, what will happen to the image? And then third one is, if it go to a point that is 2 focal lengths away from lens, here is 1 focal length away. If it's 2 focal lengths away, what will happen to the image? You can join it. This is a ray optics. So you can join it in a piece of paper, but follow what I said here. Follow the principle I said here. Okay. Okay, good. Now it's 3:51. I need to stop here. Do you guys follow me?
Yeah.
Okay.
Yep.
Excellent. Excellent.